Hi everyone and welcome to the learning curve. Today I'm going to do an illustrative lesson on hypothesis testing for single means. Here I have this problem. A professor has been teaching biology for many years. His records show that the overall mean for final exam scores is 41 with a standard deviation of 4. The professor believes that this year's class is superior to his previous ones. The mean for final exam scores for this year's class is 32 students. This class of 32 students is 44. We're going to test the professor's hypothesis at the 1% level of significance. And so one of the first determinations we need to make is that, well, is this a test of means? Yes, it is a test of means because the professor is making a proposition that the mean or average score for this year's class is greater than that of the previous year or previous years. So it's a test of means. And then the next thing we have to determine very crucially is it a Z test or a t-test? And this is going to be a z-test or z-test. In other words, it's going to be a z-test because we know the standard deviation of the population. When the standard deviation of the population is known, and moreover the sample size, which is 32, is greater than 30, which means that the data tends towards normality, then the z-test is more appropriate than the t-test. When you do not know the standard deviation of the population, then the t-test is preferred over the z-test. So because the standard deviation of the population of students sitting this exam in previous years is known, which is 4, then the z-test is what we're going to utilize. We're going to use the z-test here. And the first thing we're asked to do is to state the hypothesis to be tested. We're going to state the null hypothesis, which is that the mean mu is equal to the old or established mean that is being challenged. That's what the null hypothesis always represents, the old or established mean that is being challenged. So that's mu equal 41. And the alternate hypothesis, H1, reflects the proposition that is being put forward, represents the proposition or idea that is being put forward as a challenge to the null hypothesis. And that is that the mean is greater than 41 because the professor believes that this year's students have performed superior to students in previous years. So this therefore gives us a one-tailed test. It's a one-tailed test because the alternate hypothesis has a greater than sign. If it had a less than sign, it would also be a one-tailed test. But if we used a not equal to, it would have been a two-tailed test. But whatever sign, inequality sign we use in the alternate hypothesis depends on the specific circumstances in the question. In this case, the professor believes that this year's class is superior to previous ones. So in other words, he believes that the mean is now greater than what obtained previously, which is a score of 41. So the value in both the null and alternate hypothesis will be the same. Now, what is the test statistic? This is a z-test. So the test statistic is going to be z equal x bar minus mu, x bar being the sample mean, mu being the population mean, divided by sigma, which is the standard deviation of the population, divided by the square root of n, where n is the sample size. We're not going to do the calculation of the test statistic here. We are only stating the formula that will be used for it because that's what we're asked for. In step 3 now we're asked to draw the standard normal curve, which is a curve that shows symmetry around the origin, around the center point. So here's the standard normal curve. And the standard normal curve here is symmetric around the center of 0. Now, we need to mark a very important value on the standard normal curve, which is called the critical value. That critical value will separate the rejection or critical region from the non-rejection region. In order to come up with this critical value, we need to use the level of significance of the test, which is 1%. So the level of significance of the test is alpha equal 1%. Alpha represents the level of significance. Once it's a one-tail test, which this is, and we know it's a one-tail test because the alternative hypothesis has a greater than sign. If it had a less than sign, it would have also been a one-tail test. Once you're working with a one-tail test, you just subtract the level of significance from alpha, the level of significance alpha, rather, from 100%. So once it's a one-tail test, you subtract alpha, the level of significance, from 100% because 100% represents the whole. So 100% minus 1% gives us 99%. Yes, 99%. And then we convert that to a decimal form, which would be 0.99. So now that we have found this probability value of 0.99, we're going to look for it in the body of the standard normal table in order to determine the critical value that we will mark on the standard normal curve. So what I do here is that I go to the standard normal table and I look in the body of the standard normal table, which is where the probabilities are. What am I looking for? I'm looking for 0.99 or the closest value to it. So the closest value to 0.99 here would be 0.9901. One thing to know about the standard normal table is that the further down and across you go, the larger the probabilities shown become. So we have located the closest value to 0.99. And what we're going to do here is that we're going to identify the Z value reading, or the critical value, in other words, that corresponds to this 0.99. So what I do is that I go down in this column marked Z. These are critical values. I go down in this column and I locate 2.3, which corresponds to this 0.99. So 2.3 would be the stem of the critical value, and the tail of the critical value would be to go up column wise and locate the corresponding value here of 0.3. So basically by adding that 0.3 to the 2.3, we get 2.33. So all you need to do is to find the column and row reading for that corresponds to the probability value that you're searching for in the body of the table. So this will be 2.33. So our critical value is 2.33. So I will say here that the Z value, I'm just going to write a simple note here to say therefore Z alpha is equal to 2.33, and that's my critical value. That critical value I will mark in the tail of the standard normal curve here, as I'm doing. So I will mark that critical value here, and to the right of the critical value, and I'm marking to the right of the standard normal curve overall, and shading to the right of the critical value because this is a one-tail test, particularly a right-tail test because the alternative hypothesis says greater than. So I'll mark to the right of 2.33. Now, strictly speaking, it doesn't matter where in the right tail you mark the value, 2.33, strictly speaking, but because the values go just above 3 on both the left and right tail, the Z values on both the left and right of 0 go to about 3, then you should go further into the tail to get a good approximation. But strictly speaking, it really doesn't matter for drafting purposes. So we mark 2.33, which is obviously going to be a value to the right of 0, and shade the area to the right of it. Now this area to the right that I have shaded is the critical region or rejection region. So this is my critical region here, otherwise called the rejection region. So this is the critical region. Any value falling in this critical region that is derived from the computation of the test statistics will lead to us rejecting the null hypothesis. So it means that the unshaded area here would be called my non-rejection region. So this is my non-rejection region. Non-rejection region. Okay, so we have our non-rejection region, which is the unshaded area here, non-rejection region, and I have my critical or rejection region. So either is fine. It's going to name it here rejection region, but I could also, as I indicated, call it my critical region. So this is my rejection region here. It means that any x value that I come up with from any z value that I come up with from the test statistic will that falls to the right of 2.33 on this axis. This is an x-axis really. Any z value that I come up with that falls to the right of 2.33 will lead us to rejecting the null hypothesis. But if my calculated value from the test statistic is less than 2.33, which means that it would fall in the non-rejection region, then I would fail to reject the null hypothesis. All right, so let's show you how this is done now. So it says to calculate the test statistic. So I'm going to use the formula from step 2. The test statistic is otherwise called the calculated value. So let's come up with the calculated value now. So to calculate the test statistic, and the test statistic is going to be the crucial value that will help us to determine whether to reject or not reject the null hypothesis. So here it is, x bar minus mu divided by sigma over the square root of n. Remember now, x bar is the sample mean. X bar is the sample mean. Mu is the population mean. Sigma is the population standard deviation. And n is the sample size. Okay? So let's look at this now. So this is going to be equal to, from the question, x bar, which is the mean from the sample of 32 students, is 44. So x bar is 44. Mu will always come from the null and alternate hypotheses, 41. The value in both the null and alternate hypothesis will always be the same. So it's going to be 41 for mu. Again, that comes from the null and alternate hypotheses, divided by sigma, which is the population standard deviation here, and the population standard deviation is 4. So I place the population standard deviation there, divided by the square root of n. N is the sample size or number of observations that were included in the sample. And that is 32 students. That was the sample of students that was used for this year's class. So we're going to divide by the square root of 32. So let's do the math here to simplify this. 44 minus 41 is going to be 3. And then you can go on your calculator and simply just divide 4 divided by the square root of 32. 4 divided by the square root of 32, and that's going to give you a value of 4 divided by the square root of 32 is going to give you a value of 0.71 rounded to the second decimal place. So if you round to the second decimal place, you get 0.71. That's 4 divided by the square root of 32, and then we're going to divide 3 by 0.71. And when we divide 3 by 0.71, we get roughly 4.23, again rounding to the second decimal place. So you can generally round to the second decimal place for these problems, unless otherwise specified in the question. Now, what we realize is that the calculated value of the test statistic here is 4.23. What we now need to do is to determine whether that 4.23 falls to the right of the critical value. Here's the critical value here of 2.33. If it falls to the right of 2.33, then it will fall in the rejection region. Or does it fall to the left of 2.33, which would mean that it would fall in the non-rejection region? Well, because 4.23 is clearly greater than 2.33, And remember that the further right you go on the x-axis, the larger the values become. 4.23. 4.23 is going to fall clearly in the rejection region here because it's a bigger value than 4.33. If you got a result like 1 or 1.5 or 2, then those would fall to the left of the critical value of 2.33, which means that they would fall in the non-rejection region. But this 4.23 calculated value falls in the rejection zone or rejection region or critical region, whichever of those terms you want to use. And that means that we will reject the null hypothesis. So the final question here is, should the null hypothesis be rejected or not rejected? At all times, guys, you need to remember that when you carry out a hypothesis test, the conclusion that you're going to come up with is a conclusion regarding whether to either reject or not reject the null hypothesis. The conclusion is always first and foremost expressed in relation to the null hypothesis. So I'm going to say here, since the calculated value of 4.23 falls in the rejection region, our conclusion would be that we reject the null hypothesis. Once the calculated value from the test statistic formula falls in the rejection region, your conclusion is going to be that you're going to reject the null hypothesis. But if the calculated value from the test statistic falls in the non-rejection region, such as in this case, if it was a value like 1, then you would not reject or fail to reject the null hypothesis. But again, in this case, the calculated value falls in the rejection region, so we will reject the null hypothesis. And since we are rejecting the null hypothesis, it means by default that we're supporting the alternative. So we say, and support the alternate hypothesis. And support the alternative hypothesis. And this suggests, remember that the professor proposed that the mean for this year's class is greater than the mean for last year's class. So we say this suggests that the mean has increased. So there is support for the professor's position. So there is support for the professor's proposition. There is support for the professor's proposition or hypothesis. Okay? And that concludes this hypothesis test. So we have concluded that the null hypothesis should be rejected. The null hypothesis, which said that the mean is equal to 41, should be rejected in favor of the alternate hypothesis that the mean grade for final exam scores is now greater than 41. And that concludes this hypothesis test that we have carried out using the method of the standard normal distribution, and I'll be doing several other videos which also show other techniques of hypothesis testing. For example, I will be doing a video which shows the application of the t-test, and videos which also show the use of the z-test under different conditions. Two-tail tests, for example, as well as left-tail tests. This was a right-tail test. Thank you for your time, everybody. I hope that this was a lesson in learning for you for hypothesis testing for means. Thank you, and remember to subscribe and keep posted to the videos that I will post on this channel, which covers a range of topics in mathematics, pure mathematics, applied mathematics, statistics, and economics. Have a good one, guys. See you soon.